However, there's actually something else we can say about this that's sort of interesting, because we know something else about equilibrium. Okay, we've talked about equilibrium, and so we know something else about equilibrium that's related to this, and it's sort of interesting, and it's this. We take these two blocks, they start out at different temperatures, we put them in a closed container, we wait till they come to equilibrium, they've been in contact for a long time. At that point, on this macroscopic level, think about the problems we did with internal energy, what is it that's the same in the two blocks? Okay, so the biggest vote is for the temperature, and that's what we've been doing all semester, right? When things come to equilibrium, they're at the same temperature, and then we can calculate how much. So what about the thermal energy, though? I mean, some people wanted the thermal energy to be the same. They did have different masses, so that means they have different numbers of atoms, doesn't it? So we have this block that's a 2 kilogram block, and we have this block that's a 1 kilogram block, so this block must have twice as many atoms, right? Well, we were just making plots of the most probable situation, the most probable distribution of energy for systems like that, and what would we find with this one? Yeah, so we'd expect, 67% of the energy to be here and 33% of the energy to be here at equilibrium. Well, that energy we're talking about, that is the thermal energy. This is the energy we're putting into the oscillations of these masses and chemical bonds. So all these quanta of energy we're adding, that's the thermal energy of the system. We're increasing the thermal energy. That's what we're talking about. So the thermal energy is different just because there's different numbers of atoms in these things, different numbers of atoms and bonds. Does that make sense? Makes sense. All right. So let's go a little further with this and see if we can say something else. So we said, so here's our block with 100 oscillators and 400 oscillators. I think this is going to be easier to work with. Well, maybe not. This may be easier to see if we change the ratio. So we'll make it 3 and 200 and 300 here. Okay, so we said that at the most probable distribution, which is at equilibrium, the entropy is maximum. And we can see that from the graph. So, except I want to draw on this and I don't want it to be there. So let's see. There we go. All right. So at the most probable, we don't really need this one. The most probable situation was where the entropy is a maximum, and we said here this was, what did it say? We have block 1 has 200 oscillators and block 2 has 300 oscillators. So therefore, the most probable situation was that a 2/5 40% was in block 1, and so the maximum should be at 40%, which is right here, and that should be modulo me not being able to draw very well in this. So that's the maximum. Now, so that's what can we write? We can write down an equation describing a maximum. So we say at the maximum, the rate of change of the entropy of the total system with respect to energy, in this case we're going to call energy Q1, the number of quanta in block 1, has to be 0, right? Because that's what a maximum is. But since the entropy, the total entropy, is the sum of these two entropies, then we can say, well, because S total is the entropy of block 1 plus the entropy of block 2, so we're adding these two curves to get that one, then it also has to be true that the rate of change of S1 with respect to Q1 plus the rate of change of S2 with respect to Q1 is 0, because we're just differentiating this with respect to. So basically, this is the rate of change of entropy with respect to energy. These two things have to add up to 0. So that says something about the slopes here, that this slope is the negative of that slope, right? So these slopes have to be equal and opposite. So I don't have quite the right colors, but this slope and that slope have to add up to 0 at that location. Now there's one thing about these plots that just is a little distracting. The thing that we're really focusing on is the location, the distribution of energy where the entropy, total entropy is at a maximum, and these two slopes have to add up to 0. These curves cross, and it's just really tempting to think that this means something and it must be an important place. It's not. It's not, okay? The interesting place is here, where this one is the rate of change of the entropy of, what is it, block 1, I think. Let's see what it says. Yep. ds1 dq1, and this is ds2 dq1. But actually, think about what Q1 is. Q1 is Q total, 100, minus, Q2. The number of quanta in block 2 is Q total minus Q1. In this case, it's 100 quanta minus Q1. So we can actually do a change of variables here and differentiate the entropy of block 2 with respect to Q2. So the rate of, if the entropy of block 2 is decreasing as Q1 increases, then it must be the case that it would be increasing as Q1 decreased, or increasing as Q2 decreases. So basically what we've got here is the rate of change of, let's actually write this over here. The rate of change of entropy of block 1 with the amount of energy in block 1 is actually equal to the rate of change of entropy of block 2 with respect to energy at this location. So this is actually equal to minus ds2 dq2. So the rate of change of each of these entropies with respect to energy at the most probable situation is equal. Well, you just said that the temperature was equal at the most probable situation. So it looks like these derivatives, the rate of change of the entropy of an object with respect to the amount of energy in the object, how much the entropy changes as you put in energy, and this of course has to do with the number of oscillators. Those things must be directly related to the temperature, because these are equal at the time the temperature is equal. So we're very close to a definition of temperature. So we have these curves. And we saw that we think that the slope of the SDE, we wrote DE here, where we're talking about energy in units of joules instead of in units of number of quanta, but they're related. And the question is, we saw that the block with the bigger slope was gaining energy, and the block with the smaller slope was giving it away. So which of those statements makes sense? You want to go back and look at those curves? You've got it, all right. So remember that the curves look kind of like this. Let's see if I can draw one carefully. We have, this is Q1 and this is so remember the plot of entropy versus amount of energy for a block, a single block, kind of looked like that. So think about where the block is cold and where it's hot. We're not good. Okay. So this is the entropy of block 1, okay, and this is the amount of energy in block 1. So is block 1 hot when Q1 is big or Q1 is small? Big. So block 1 is hot over here, and it's cold over here. Here's the slope of ds1, de1 here, or dq1. And here's ds1, dq1. So when the block is cold, the slope is large. When the block is hot, the slope is small. Well, no, the maximum, I mean, the entropy is increasing because as you put more energy into the block, there's more ways to arrange the energy. But we're interested in, it's hot because there's more energy in it, right? Okay, so it looks like that's cold when that's large slope, and that's smaller slope, and it's hot. So in fact, it looks like it's an inverse relationship. And so we've got the following definition. It turns out to be that it's 1 over the temperature, which is equal to the rate of change of the entropy of an object with respect to the amount of energy in that object. So if the entropy's increasing rapidly as you put energy in, this object must be at low temperature. If it's increasing slowly, it must be at a high temperature. Now we're lying just a little bit here because energy actually isn't the only variable we've got here. And so what this really ought to be is the partial derivative of S with respect to energy, where a bunch of other things like volume are held constant and things like that. But it's close enough to say basically that the rate of change of entropy with respect to temperature with respect to energy is in fact the temperature. Okay. So, can we calculate something? Okay, we have a system. We transfer 5,000 joules into it, this object. That's thermal energy increase. And we find that the entropy of the system increases by 50 joules per Kelvin. What's the temperature of the object? Approximately. So we're approximating a derivative with a finite difference here, but we've been doing that all semester. Okay, so you said 100 Kelvin, so how do we do this calculation? Well, looks like what we want is if 1 over T is approximately the change in entropy with respect to energy, then temperature is going to be approximately given by delta E over delta S. And so it looks like we have 5,000 joules divided by 50 joules per Kelvin. Notice the units are going to come out in Kelvin. That's a good thing. And so that does indeed look like 100 Kelvin. Right?